Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will continue talking about loss functions. We spent last lecture, and I think part of the lecture before that, discussing how we can construct loss functions for any type of problems. We went through one example last time, which was the regression problem, and we saw that with the steps that we had, we reached the least squares function that we already know from before. To make sure that you are on the same page with me, let's go through these couple of questions. The first one, among the steps of constructing a loss function, which of these? How many steps we discussed last time? 4. Yeah. So among these 4, which of these are correct? Choosing a suitable model for the problem. Choosing a suitable probability distribution for the problem. But why not the first one? Are we actually choosing a suitable model using the loss function? We are trying to find a model, okay, to find a good model, okay, but we are not choosing the model among neural networks and linear regression and so on. That's not the purpose of constructing a loss function, but we choose a suitable probability distribution. This among the steps, right? How about the other two? Are these among the steps also? Set the model to predict its parameters. Its here refers to the model, right? We don't actually set the model to choose to predict its parameters. How about the last one? Do we set the model to predict the parameters of a probability distribution? Yes, that's among the steps, right? The second and fourth, yes, second and fourth. Okay, the second question: why do we need a loss function? What's the purpose of having a loss function? Think, please, before you answer. Do we need a loss function to predict the parameters of the probability distribution? No, that's not the purpose. To learn the parameters of the probability distribution? No. To predict the parameters of the model? We don't predict the parameters of the model. We learn the parameters of the model using a loss function, right? How about the last one? To predict the output of the model given an input? Is that the purpose of a loss function? No. We don't need a loss function to just predict the output of the model given an example or input, but we needed to learn the parameters of the model. Okay, and that's what we will see inshallah next lecture. Okay, how we can do the training. This lecture inshallah will continue taking I think 2 or 3 more examples of constructing loss functions for different types of problems. Okay, yes, the answer is the fourth one. Okay, if you remember last time the example that we stopped at, we were talking about a regression problem, which is estimating the price of a house given some information of the house, and because it's a continuous output, we assume that the probability distribution that we will choose is the normal distribution, and the normal distribution has 2 parameters, the mean and the variance. At the last lecture, we assumed that the variance is constant. Okay. And when we did that, we got the loss function to be reduced to the least squares function, right? Because we, if you remember here, we just take the log of that factor, which is constant, so we get it out of the minimization function. So eventually, we didn't have any variance. Okay, in the loss function. But we could have learned the variance. So we could have used the original loss function. This is the original loss function that has the mean and the variance before we reduced it to the least squares function. And it has plugged in it the mean and the variance. Where is the mean? Here in that loss function. How did we get this loss function? How did we get this expression? From what? No, the whole expression. From, let's say from here. Okay, let me change this. So this part, how did we get this part? What is this? The probability from which distribution? The normal distribution. So that's the probability density function of the normal distribution, right? Right. The probability density function of the normal distribution has two parameters, right? The mean and the variance. The variance is here. Where's the mean? It's this part, right? Now, didn't we say that we will set the output of the model to predict the mean? Okay, so that's actually the mean. But the mean here is predicted. The mean here is predicted. Is the actually the output of the network. Okay, but before in the last lecture we said that the variance is constant, and we don't care about the value of that variance. Okay, but if we care about it, then we can learn it. Okay, so we can keep it in the loss function, and we can learn it along with the parameters of the model. So remember, here we had just phi. Okay, so we minimize that function. Okay, we get the values of phi that will minimize this function. Phi is what? Is the parameters of the model, right? The weights and the biases. Here we say, okay, we are also interested in the variance. We want to predict the variance, not to predict the variance. We want to learn the variance. So we will just deal with it as if it is one of the parameters of the model. So during the training process, which we'll not talk about this lecture, inshallah, next lecture, and the next week, we will learn how to learn the parameters of the network. And in that case, we will also assume that sigma square is one of the parameters of the model. So we will learn it along with the other weights and biases. Okay, and that's why here we cannot get rid of sigma square, because we want actually to learn it. So we will just keep it in the loss function. And we will learn the optimal value for the variance that will minimize this original loss function, the negative log likelihood loss function. Is that clear? So before, we assume that the variance is constant, and we are not interested in knowing the value of that variance. Okay, so we will not optimize the network for a specific value of the variance. We will not get an optimal value for the variance. We just assume that it's constant. Here we also assume it's constant, but we will learn an optimal value for it. Okay, so we will have to keep it in the loss function. So we will have to keep the original form of the loss function. We will not be able to use the least squares function now. We have to use the original one, okay, which has the variance in it. Okay, so now the model predicts the mean, and the variance is learned. What's the difference between learned and predicted? Predicted means one of the output will be that value of the network. Okay, but learned is just one of the parameters of the network, like the weights and biases. Okay. Yes. Yes. But also. But it's unknown, so we will learn it. Yes. But while we're learning it, we're also learning the parameters of the model. Yes. So changing it, while changing the parameters of the model, will have. They will interact. Yes, of course. Yes, it is like the other weights and biases. So it's not a constant. No, it is constant, but we will change it through the training to get an optimal value for it. Now, the weights also, as we will learn, inshallah, from next lecture, the weights and biases will change during the training until we reach the minimum, right? The minimum of the loss function, right? They are considered constants that are learned, right? No, parameters. We will not be. We cannot call them constants. Yeah, after training, they are fixed. Then the same for variance. Yes. Yes, because in this case, yes, it would be a parameter. Yes. Okay, but we learn one value for it. That's why we're saying it's constant in inference. Okay, yani after training. Yes. Okay, any other questions? Right. In this case, when we assume that the variance is constant, we call it homoscedastic regression. Homoscedastic regression. Okay, when we assume that the variance is the same everywhere. Everywhere means what? With any input, the variance will be the same. So if you look at this plot, you will see that this is the input, and for each input, the output is one value, but it has a range of values. Okay, so here we are actually plotting the mean that the network predicts and the variance that is constant. And you can see that the width here is the same everywhere. Okay, remember when we were doing something like this, right? So here we don't plot the entire distribution, we just plot the mean and 2 sigma actually, okay, which covers most of the probability of the distribution. So you can see that here, you can see that the you can see that the predicted value is different with different inputs, right? The mean is different, right? Because we in this network we predict the mean, but the variance is not predicted. Okay, it's constant. So whatever the output will be, it will be the variance will be constant. Okay, so we call this homoscedastic regression because we assume that the variance is constant, is the same whatever the input is. Type. What if we assume that the variance changes with the input? This is called the heteroscedastic regression. Now we want to predict both actually. Okay, we want to predict the mean and the variance. So look at the model now. You will see that we have 2 outputs, one for the mean and one for the variance. Now, why? So we saw this before, right? The mean equals the output of the function. Why is it F1 here? Not the first layer, it's the first output. F means always the output of the network, right? Because it represents all the network as a function, right? So here we have 2 outputs. We are predicting 2 things. Remember in the beginning, in the steps of constructing a loss function, we said that we will first choose a probability distribution, then we set the network to predict one or more parameters of the probability distribution, right? We started with only predicting the mean. Here we will see what if we also predict the variance. Okay, so F1 will be the first output of the model, which is the mean, and then F2 will be the second output. Now, why do we square this? Yes, because the variance is always positive. Okay, the network, the output of the network is not guaranteed to be positive. It can be anything. Okay, but to make sure that it will be positive, we square it. So the square of the second output will be the predicted variance. So now you know why we are squaring, right? And this is now the loss function. In the previous slide, we had f of x and phi, which was mu, right? And we had sigma. Now sigma is predicted with, or sigma square is predicted with the square of the second output of the network. So you will see it here, and you will see it here. Okay, so now the loss function has both predicted value. And the model now, the network now has 2 outputs, not just one. Type. What is the effect of that? Now, remember in the previous slide when we saw the plot, okay, the variance was the same everywhere. Now, because for every input we predict the mean and the variance can change. So look at the value for this, the output for this value. You see the variance here. Okay, look at the output for this value. You see the variance here. Are they the same? No. For every input, the mean will be predicted and also the variance will be predicted. Okay, that means that the certainty or uncertainty of the network, of the model, will change, of course, with the input. Okay, given input, the probability distribution will be different, not only different in the mean, like what we saw in the previous lecture. Now it's the mean and the variance, the center of the distribution and also the width of the distribution. Better, you mean faster in training? Because now we are predicting two things instead of just one, so it will take more time to converge. But of course, it will provide more information, right? And eventually, instead of just saying this is the mean, no, I can say this is the mean, and this is how confident the model is about that mean. And if the variance is very small here, is does that mean the network is more confident than this or the opposite? Which one is more confident? The smaller one, right? Smaller one. The network is, regardless of whether this is the correct answer or not, right? So the model can say this is the output, and I'm very confident of it. Maybe the output is wrong, okay? But I'm talking about the confidence of the model. Okay, now the confidence is indicated by the variance to some extent, yes. Okay, you remember that we are trying to predict a probability distribution for any given input, right? This probability distribution is determined by two parameters. So the shape of the distribution is determined by two parameters, the mean and the variance. So we are trying to predict it more accurately. Previously, we just said the mean. Now it's the variance. Okay? Yeah. Whether how it is a function of the input, it depends on the data that we have. Right? Eventually, each one, as you remember from what we studied before, every output is a function of the entire thing, right? Function of the input and function of the entire network, right? So both in this case, the mean and the variance will be functions. It depends on the problem. Okay? Of course, different functions. These are different outputs, right? They will be different functions, right? Different what? If we have a ReLU activation function, different piecewise linear. You forgot different piecewise linear functions, right? Of the input. They are different, of course. Okay. Okay. Any questions so far? Remember that the loss function is a summation over what? What is that summation? Over the training examples, over the training data. Every single, what is I here? I is an index of the training examples, right? 1, 2, 3, over all training examples. So of course the training examples affect the learned parameters. Okay. Type one quick question. Why, you remember in the previous slide we had phi hat and sigma square hat. We don't have it here. Why? Yeah, the sigma square is not learned now. Okay, it is predicted. Okay, it's not a parameter. It's an output of the model. Okay, is that difference clear? Okay, so sigma square now is not learned. It is predicted for every input. Okay, now switching to the second example, which is binary classification example. Okay, here's the example that we saw before. I think in the very first week of the course. Given a review, I want to predict whether this review is positive or negative. Okay, type. Is that a regression problem? Why not? Yeah, the answer is discrete actually, right? It's a discrete. Okay, type. How many possible outputs? Two possible outputs, but of course we will have just one of them. Okay, so this is called binary classification. Binary classification. So the goal here is to predict which of two classes, 0 or 1, the input belongs to. Type. Now we want to construct a loss function, right? We want to construct a loss function to train a model for that problem, right? What's the first step? The right probability distribution. Okay, now the output is discrete and we have two classes. Okay, so one of the common probability distributions that are suitable for that problem is the Bernoulli distribution. Bernoulli distribution has just two values. One probability, the first probability or the first value is the probability for the positive class, which is called lambda, and the other one is the probability for the negative class. So when the output is 1, I mean when the value of the variable here is 1, then the probability is lambda. When it's 0, it's 1 minus lambda. Okay, so this distribution, which you see it here on the right, has how many parameters? Just one, lambda. Okay, because once I know lambda, I know the probability of the positive class and also the probability of the negative class, right? Because one is 1 minus the other, right? With me so far? Okay, so this is the probability distribution function. It's 1 minus lambda when y is 0 and lambda when y is 1. Okay, we always like to have just one expression that represents the probability distribution. So from here, we can get this expression. This is equivalent to that one. So this is actually the probability distribution also function for the Bernoulli distribution. It looks complex, but it is equivalent to this. How? If y is 1, what should be the probability? From here, lambda. Let's see from this expression. If y is 1, this is 1 minus 1. So this is 0. Anything raised to 0 is 1. And it will be lambda to the power 1. Right? So it will be lambda. If y is 0, this one will be 1. And this one will be 1. So it will be 1 minus lambda. Right? So this is exactly equivalent to this when y is 0 or 1. Okay? And it will be easier to use because it's just one expression. Type. What's the second step? So we got the probability distribution, right? What's the second step of constructing a loss function? Set the model to what? To predict the parameters of the probability distribution, right? What are the parameters of the probability distribution here? Just lambda. What's just one parameter, right? One parameter. Type. Now we will set the network to predict lambda. Type. Set the output of the network to predict lambda, right? Type. Is there any restrictions on the output of a neural network? Yani, let's say that we have just one neuron at the output layer. Is there any restriction of the values of that? Can it be any negative or positive value, or it's always positive or always negative? In general, without any activation function, is there any guarantee that it will be positive or negative? No, it's unbounded, right? Type. In our case, we want to use it to predict lambda. Is there any restriction of the values of lambda? Is it positive only? Is it 0 or 1? It's a probability. So it is it's between 0 and 1. It has to be between 0 and 1. Right? So we'll have to force the output of the network to give a value between 0 and 1. Okay? Without anything, it can be any value. Right? So the output of the neural network can be anything. But lambda is between 0 and 1. It's not 0 or 1, by the way. Okay, it's not 0 or 1. It's between 0 and 1 because it's a probability. Type. How can we do that? One common way to do that is to use the sigmoid function. Yes. Okay, the sigmoid function. So the sigmoid function takes any input and converts it to a number between 0 and 1. So this is the sigmoid function. Okay, it takes any input from minus infinity to infinity and gives a number back between 0 and 1. And that number now can be considered as a probability, right? Because it's between 0 and 1. So let's look at the extremes of that function. When, or actually some values of that function. When the input is 0, so this function is 1 over 1 plus e to the power minus the input. Okay, so when the input is 0, e to the power 0 is 1. So 1 over 1 plus 1, half. So when z is 0, the output is half, right? The value is half. Type. When z is minus infinity, what happens? Minus infinity is what? Is infinity, right? E to the power infinity, infinity. 1 plus infinity, infinity. 1 over infinity, 0. Okay, so at minus infinity, it is 0. Type. On the other extreme, when z is infinity, minus infinity, e to the power minus infinity, no, e to the power minus infinity is 0. So 1 over 1 plus 0 is 1. Okay, so it will be 1. So the lowest value will be 0 in minus infinity. The highest will be 1 in infinity. Okay, see, so it compresses any input to a number between 0 and 1. Is that good for us? Yes, so we'll take the output of the network, which is f of x and phi, and apply it to, or pass it to the sigmoid function. Okay, so lambda now will not be the output directly like mu before, right? So why didn't we do mu? We do that with mu, with the normal distribution. Yeah, because mu can be anything, can be negative or positive, can be anything. Okay, so before we said mu equal the output directly, but now we cannot do that. We have to apply another function that will make sure that the value will be between 0 and 1. So lambda here is the sigmoid of the output of the network, and this is called the sigmoid activation function. Okay, it is one of the activation functions. It can be used actually in replacement of ReLU or anywhere, but usually we use it at the output. Remember when I told you that sometimes the output we will apply an activation function? This is one case. Okay, when we want to make sure that the output is within a range. But actually the sigmoid can be also used anywhere in the network. It can be used instead of ReLU. Okay, ReLU is better in terms of training. We'll talk about that later, inshallah. But theoretically, it can be used anywhere. So it is an activation function. Okay. So if we do that, then this is the actual probability distribution. Now we will replace lambda with the sigmoid of the output. Okay. So now this is the probability distribution when we predict the parameter of the model. This is to show you the effect of adding the sigmoid function. Let's say that this is the original output of the network that is not limited. Okay, it can be anything. And now when we apply the sigmoid, it will be something like this. Okay, so first of all, it is compressed between 0 and 1, and it is smoother. So if you, for example, look at this value, so this is when x is, what is 0.4, I think. When x is 0.4, y is, or the output of the network is minus, that's 0.5 probably. Okay. Okay. So for the same point of x, you will see that the value of y now is between 0 and 1, is less than 0.5. Okay, because the input is negative. And so on. So for every input, we have the direct output of the network, and then the direct output is passed to the sigmoid function. Okay, so the output will always be between 0 and 1. So this is lambda, and the other dotted one is 1 minus lambda. Remember, it's two probabilities, right? But we don't need to compute both. We just compute one, and the other one is 1 minus that one, right? So yeah, we'll talk about that, okay, in a couple of minutes. Okay, but that's the effect of the sigmoid. So for every input x, we have a probability distribution. Where is that? And remember, this is the idea, right? that for every when we use a probability distribution and we set the network to predict the parameter of that distribution, at every input we have a probability distribution, right? So now for every input, this is the value of lambda, which determines the probability distribution, because the probability distribution is just two numbers: lambda, which is the probability of the positive class, and 1 minus lambda, which is the probability of the negative class. Okay, so in that case, as you see here, lambda is very small, right? It's like 0.2. So that's 0.2 and that's 0.8. Okay, now that's the distribution for given input. Okay, are you following with me? Any questions? Right. The third step is to construct the loss function. Now the loss function is the negative log likelihood function, of course, as usual. This is the original probability distribution function. We just take the log of that and multiply by minus 1. When we take the log of that, what happens? This is a multiplication of two things, right? So it will be the log of that plus the log of this, right? The log of this is what? This is a power, right? So we get the power before the log, right? So this is something like if we have log a to the power b times c to the power d. What is this? This is log a to the power b plus log c to the power d, right? Which is, yeah, so b will be here. So b log a plus d log c. And that's exactly what we did here. Okay, so you will see 1 minus y, which is this, log this, same, right? Minus y, which is this one, log this, which is this one. So again and again, I think I asked this question maybe 4 times now. Why this is yi? Why this is yi, not just y? Yes, and yi for the training example is the correct class, the correct label, the correct value. Okay, so remember from the beginning of that session, we said that we want to maximize the likelihood of the correct output. Okay, so we want the probability of getting the correct output to be higher. Okay, so the loss function will always be a function of those values, yi, which is the correct output of the training example number I. Okay, is that clear? And this is this loss function is very widely known. Okay, it's called the binary cross entropy loss. Okay, now I want you to understand more this loss function. Okay, this summation is over the training examples, right? So let's look at only one example, the loss value for one example only. This is the summation of the loss values for all examples, right? Let's take one example, which is example number I. Okay, and see what's the meaning actually of this function. Now, in this problem, this is binary classification, right? So we have two possible values of the output, right? 0 or 1, positive or negative. Okay, type. If the correct output is 1, that means yi is 1. Now, yi is the correct output. Okay, so yi is 1. What happens to this expression? This part will be 0. So all of this is 0, خلاص, right? Then minus yi is what? Is 1. So this is crossed, that's 1. And that will be log of this value. Okay, type. What is this value? What does it represent? which is, we call it what? Lambda. This is lambda. Okay? Huh? Yeah, well, this is coming from Bernoulli distribution, yes. So that means that when yi is 1, this whole loss will be what? Will be minus log lambda. What is lambda? That's the probability of the positive class, right? Which is the correct one here. So when yi is 1, the loss will be minus log the probability of the class, the correct class, the positive class. So let's see when yi is 0, what will happen. When yi is 0, what will happen? This one is crossed, right? Okay, and now this is 0, right? So now all of that is 1. So it will be minus log. Can you tell me? Minus log? 1 minus lambda. Very good. 1 minus lambda is what? Is the probability of the negative class, which is the correct one here. Okay? So although it looks really complex, but it is one of two values. It's minus log lambda when the correct label is positive, and minus log 1 minus lambda, which is the probability of the negative class, when the correct label is negative. So overall, it is always minus log the probability of the correct class. Right? So it's much easier than it looks. It's just minus log the probability of the correct label. So if the correct label, if the model managed to accurately predict the correct label, it will give high probability for that, right? Right? Yani if the network predicted the correct label with the high probability, that means that it's more confident, right? It's more confident about the correct class, right? In that case, the probability will be very high, right? So the log of it, yeah, let's say the highest value of the probability is what? Is 1, right? So log 1 is 0 if the correct class is the positive class, right? So that will be 0, right? So the loss in this case will be 0. If the network predicted the correct class, it will be 0. And here also it will be 0, right? So always it is minus log the probability of the correct class. If the probability of the correct class is very high, then the loss will be very small. Okay? That's the cross entropy loss. Is that clear? Okay. The last step, the inference. Okay? Now, let's say that we train the model. How can we make a real prediction, a final prediction, whether the label should be positive or negative? How can we do that? So we have a probability distribution. We always get the output that will have the maximum probability, right? So the probability lambda means the probability of the positive class. So if lambda is greater than what? Is 0.5, greater than 0.5, then this is the maximum probability. Then we will predict positive label. Otherwise, negative label. That's it. Okay, so we'll choose y equal 1 when lambda is greater than 0.5 and 0 otherwise. Okay, is that clear? Okay, so that's the end of the second example. So the third example is multi-class classification. What do you mean by multi-class classification? Multiple classes, right? We have multiple classes, not just two. So here's the example that we saw before. We have an image, and we want to predict which object is in that image. Okay? So we have so many classes here. But how many outputs we should have? Just one. So it's multi-class, but it's just one. So it's univariate multi-class classification. We want to predict which of k classes the input belongs to. Type. Now we want to construct a loss function. What's the first step? Distribution. What is a good distribution for that? A distribution that will give a probability for each class, right? The previous one we had, this is discrete again, but instead of 2 classes, we have k classes. Okay, so the distribution that have or that give us a probability for each of k classes is called categorical distribution. Okay, instead of just 2 bars here, we have k bars. One probability for each class. By the way, you saw the example here, right? The previous example, right? These classes can be really so many. It can be sound and sometimes millions. And I will give you example that you are very aware of. ChatGPT. In ChatGPT, what happens? It predicts the next word, right? The next word. Type. What are the possible next words? Any word in English, right? Or Arabic or different languages, right? How many are they? Really? Okay, we'll buy that. Okay, so many classes, right? Each word is a class here in this case, right? So that's a typical example when you have so many classes. Right. Again, back to our example or back to our process. We choose a probability distribution, so the distribution will be the categorical distribution. It has k parameters. What are the k parameters? The k probabilities, right? One probability for each class, right? We have different classes, right? We have k classes here: bicycle, car, human, cat, dog, chair, right? In the image, it can be anything. So many classes. So the distribution here has k parameters: lambda 1, lambda 2, lambda 3, up to lambda k, because we have k classes. Type. That's the distribution, right? Now the second step is to set the model to predict the parameters of the distribution, right? Type. We have k parameters, so we need to predict all of them, right? Because we cannot just predict few of them, we have to predict all of them so that we can know which class, right? Type. Is there any restrictions on the values of those parameters? What are the restrictions? The sum of them is 1. That's it. So the values مثلا can be 10 and minus 9 and yeah, so 2 conditions. Each value has to be between 0 and 1, and the sum of them is 1. Okay, the sum of them is 1. So again, the output of the neural network can be anything, but the parameters has to be between 0 and 1, and the sum of them has to be 1. Okay, and to do that, to force the network, the output of the network, to be like that, we use the softmax function. The softmax function. So the softmax function takes any list of values and converts them to values between 0 and 1 that sum to 1. Okay? How does it do? So if I have, let's say I have let's say I have 3 values, okay, A, B, and C. To use the softmax function, I will convert each of these to a value between 0 and 1, and they will be summed to 1. How is that? We take the exponential power to them, to each one. So this is e to the power A, e to the power B, e to the power C. If we do that, each value now, no, it's not between the 0 and 1, it's positive. It will be positive, regardless of the value, regardless of the original value. Because remember the exponential function, we talked about it, I think 2 lectures ago, it's always positive. Okay, so now we converted the values to positive values, but they are still not between 0 and 1, and still their sum is not 1. How can we make them between 0 and 1 and sum to 1? Very easy. We divide each value by the sum of them, the sum of the exponential values. So this will be e to the power A over e to the power a plus e to the power b plus e to the power c, and so on. Now, each of those values is between 0 and 1, and they sum to 1. Okay? This process is the softmax function. Okay? So softmax of k, softmax k of z means the value for the number k. Okay? So it will be e to the power z of zk, which is one of these. Let's say مثلا this one, to e to the power c, over the sum over e to the power each one of them. Okay, that's exactly what we did here. Okay, is that clear? K is the specific one of them. K small. Okay, because there is K small and K capital. Okay, K small is the specific one. يعني مثلا here softmax, let's say مثلا we have 1, 2, 3. Okay, so softmax 2 in this case is this one. That's the second, the softmax value of the second output. Okay, is that clear? Okay, any questions? Capital K, what's capital K here? The number of categories, classes. Yes, very good. Number of classes. Right. Now plug it back to the probability distribution. Now the probability of the class K is the softmax value number K. Okay. So in this case, the output of the network, and let's say this is the network, multiple layers. Okay. Input here. And the output of the network will be how many nodes? K. Okay, let's say K is 3. So that's the output. Okay, so the network will be all of that, and then we have output. Okay, and these three values are passed to the softmax function. Okay, so remember the expression, the mathematical expression of the network? All of that will be inside the softmax function to give us the final K values. Here's the effect of adding the softmax. Let's say that this is the original output. Okay, so that's the original output. And applying the softmax function, we'll get something like that. One of the properties that you will notice that with the softmax function is that it takes the maximum value and amplify it much more than the other ones. And look at this case. Okay, you see here when x is whatever the value here is 0.6, this is the value of this is the predicted output, raw output, direct output of the network for the orange class. That's for the green and that's for the gray. Okay, if I can see the colors correctly. Okay, now you see that difference. That's not a big difference, right? When we apply the softmax, you see here, you see this value. What's the difference between this value and that value? Okay, much bigger than it was. Okay, and that's why it's called softmax. It's making a soft change to the maximum. It's not exactly the maximum, but it amplifies the maximum. Okay, much more than the others. And of course, the three values of these is sum to 1. Okay, so you can see the least of them, although it was not 0, right, and it was not very far from the other two, but now it's very close to 0. Okay, with the softmax. Okay, and for one input, again, every input will give us a probability distribution, right? So we have k values. So for this input, we have k values, the k probabilities, this one, and this one, which are represented here in that distribution. Okay, so the orange class is having the highest probability, then the green, then the gray. Okay, question? Probability. Yeah. Okay, we will do the inference. We'll see in the inference. So remember, we are predicting a probability distribution, right? So for this input, we are predicting this distribution, right? What will happen in the inference? There are three classes only, yes. Yeah, here we're assuming the three classes, of course. Yeah. Okay, we'll see in inference what will happen. Okay, before that, let me tell you that this is also called softmax activation function. Sometimes we call it activation function. It's not usual to do that in the hidden layers. Okay, you can, of course, but it's not usual to do that in the hidden layers. Usually we do that at the output layer. And because it takes all the values, okay, we even sometimes call it a layer, softmax layer. So when, inshallah, in the second half of the course, when you use PyTorch, you will see that in the code, you will add the softmax layer, okay, which means apply the softmax function to the output, all the values of the output. Okay. Right. The third step is the loss function itself. Okay. So the loss function, again, it will be the probability from the probability distribution function, which is now the softmax value. So it will be minus log softmax value for the correct class. Okay. So that's the loss function, right? So when we take the log of the softmax, remember the softmax is e to the power something over the sum, right? If we take the log of this, what will happen? It will be zk, right? Because that's log of exponential. So it will be zk, which is actually this output. Okay. Remember, before we take the softmax, this is the direct output of the network. So this is the output of the network at the correct class minus log this part. Okay. Which is the summation of all the exponential values. Okay. What is fk here? The output number k, the network output number k. We have k outputs, number k small. Okay, I think it should have been another symbol. Maybe it would be easier, but k small is the class here. And what's fyi? Yeah, that's the output network for the correct class. The output of the network for the correct class. Look at the loss function here. This is the loss function, right? Right? This minus sigma log of the probabilities, of the probability of the correct class, right? This one is what? That's the probability of the correct label. Yeah, probability, the probability that the network assigns to the correct class. And the network doesn't know the correct class, right? But in training, we know the correct class. So this is the probability of the correct class. So actually, for every input, now this is sum over all the input examples, right? For every input example, the loss for that input is just minus log the probability of the correct class for that input. Didn't we see that in the binary classification? We said that it's minus log the probability of the correct. That's the same here. It's the likelihood function, right? It's the same here. So back to your question, if the network predicted the correct class with very high probability, what will happen? It's great, yes, but in terms of loss function, what will happen? Because what's the best probability that the network can assign? No. For the correct class, what is the best probability? 1, right? Log 1 is 0. So the loss will be 0. Type. So well, that's perfect, right? Because the network actually assigned the highest possible probability to the correct class. Type. What if the opposite? The network assigned a very bad probability for the correct class. Let's say 0. Okay? Or almost 0. Log 0 is is minus infinity actually. So this one, yeah, this log is minus infinity. Okay, minus infinity is infinity. So the loss is very high. Of course, it won't be zero. It will be something above zero, so it won't be infinity. Okay, so but it will be very high. Okay, did I answer your question now? So it depends on the probability that the network will assign to the correct label. It doesn't actually. You cannot say it doesn't depend on the others because the probability of the correct label depends on the others. How is it computed? It's a softmax using the sum of all the others. Okay, so it depends on the others. But if it's very sharp, يعني the network assigned most of the probability to the correct class, then the loss will be very small. If it's really the probability is distributed among many classes, then the loss will be high. Okay, and again, it's called cross entropy loss, and because we are using multiclass, this is multiclass cross entropy loss. Okay, so cross entropy loss is very widely used in classification problems. Okay, you will see it one of the most commonly used ones. Yes. Say it again. Okay. F of x and phi. What is this? F of xi and phi. What is this? No, that's not the model. That's the output of the model when the input is xi. Okay, so that's the output of the model when the input is xi. Type. Okay, do you agree with me? That's the notation that we use. Okay, now when we say FYI, I think this is your question, right? Okay, when we say FYI, what does that mean? Forget about YI. Let's say F1. What does that mean? The first output of the network. The network has actually how many outputs here? K, because we have K classes. So F1, F2, F3, up to Fk. Type. In the loss function, we focus on the correct class, the probability for the correct class. That's why it's called FYI. YI is the correct class for the example number I. Okay? Clear now? Other questions? Okay. Now in inference, I think we answered this question, right? When we do inference, what should we do? Given an input, we will compute all the probabilities. Type. Will we provide the probability distribution to the user? No. What should we provide? The label that has the maximum probability, right? So we will choose the class with the largest probability. If we have a tie, okay, special case, deal with it depending on the problem. Okay. Okay. Type. To make sure that it's clear, let me ask you this question. For the object detection problem of 5 classes, for a given input, the network outputs what will be the output of the network in this case? Is it 1 number? Is it 5 numbers? The last one, 5 numbers, which are the softmax values of all classes, right? So is it five numbers or 1 number? 5 numbers, right? Type. Is that the only one that's correct? The last one? Yes. So of course the output will be the softmax values of all classes. Can we say that these are the probabilities of all classes also? Yes. We consider them the probabilities, right? Yeah. So no, the softmax is the probability. Okay. Type. For the object detection problem of 5 classes, A, B, C, D, E, so we have 5 classes now, and these are the names of the classes. For a given input, the network direct output was 1, 2, -1, 3, and -2 for the classes respectively. We just said that we have 5 outputs, right? I mean the direct output. Okay, direct here. Direct output is before the softmax. So 1, 2, -1, 3, and -2. Assuming the correct output is C. So for that input, the correct output should be C. So it should be class C. What is the loss of that input example? We just mentioned that 5 minutes ago. For a given example, how will we compute the loss? Okay, it's always will be minus log the probability of the correct class, right? What's the correct class here? C, right? Type. So it's minus log probability of C. What is probability of C بقى? E to the power minus 1 over, which is e to the power 1 plus, that's it? Very good. Okay, so it will be minus log this value, whatever this value is. Okay, is that clear? Now, what happens if we have other types of data? What do you mean by that? The output is different than what we saw. Now, we saw how many examples? No, 3. 2 today and 1 last time. So we have 3 examples. But that's not everything, right? That's not everything. The output types might be different. So for every output type, which means every different problem, we'll have to pick a distribution. Okay, so this table in the textbook gives us some examples, and inshallah we'll see 2 examples at least in the homework, inshallah, in homework 2, inshallah. We'll continue next time, inshallah. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.